then at some point the grain started growing in the FCC structure. Another grain started growing from here, and when the two hit each other, they stopped growing. So I got my grain size based on when this hit that, or which are the two nucleation sites. Now, if I put aluminium, the number of nucleation sites increases. So I will have one nucleation here, immediately I'll get another nucleation, the two will touch quick. So the grain cannot become big. So I get a finer grain size. So it helps in the nucleation of fine grains. Okay. Now this is one of your queries over here. So types of heat treatment, you tell me. Quench. Quench is the process, hardening is what happens. Tempering. Tempering, post-well heat treatment are similar, not exactly the same. And solution. Post-exhaustion. Okay, so let's understand now. You got some idea of the diagrams. Let's understand that when we do each of these, what is happening? What are we trying to do? So heating a, see, when I use this term hypoeutectoid steel, it means the steel having less than 0.8% carbon, which is all our steel. So all the steel we are talking about practically are hypoeutectoid. Eutectoid is the 0.8 line. Hypo is below, hyper is above. So hypoeutectoid steel, 30 to 50 degrees centigrade above the critical point A3, holding at this temperature and slowly cooling in the furnace. Okay. Annealed material would have lowest hardness, lowest strength, low toughness, and maximum ductility. Tell me, in a pressure vessel steel, what properties do you want in a pressure vessel steel? What are the properties we are looking for? Who makes steel specifications? Who is making the steel specifications? ASTM. ASTM. ASTM has got million specifications. Why ASME has to again make another list in the code? Service dot talk with ASME. Not that in sense of chemical or anything like that, but pressure vessel specific. ASME is a pressure vessel code. So those materials that are good for pressure vessel use are picked up from ASTM and they are put in and ऐसे करके ASTM. Okay. So what are they looking at? When they pick up, suppose you are here picking up, I got a list of ASTM materials. I want to see which is good for making pressure vessel. What will you look at?
Mechanical property, mechanical property.
Agreed. And what mechanical properties? Let's be specific.
Tensile,
toughness,
hardness, impact,
hardness, impact, toughness. The toughness. And
microstructure.
someone said no. Microstructure, unless I don't find aluminium, I'm happy to call that.
Elongation.
But in which formula does elongation come in your calculation? Does it come anywhere? Here, when I'm finding thickness of a pressure vessel, do you check design somebody? You don't check design? No calculation of pressure vessel. Okay. So what we do is what we talk about is allowable stress. You have heard that term? What is it?
There are maximum allowable stress.
No. What is allowable stress? What is stress? Come on, let's go to basic. What is stress?
Force upon area. Force per unit area.
Load upon area.
Yeah. Thank you. Load upon area. That is stress. Okay. So now you said I will check. What you will check? Tensile strength. And No one said yield strength, no?
Yield is-
Yield also you'll check.
Yeah.
Okay. Then what you do with it?
Compare with the requirement, what is specified in the.
Now, listen.
Specification.
That's why I asked you, do you know design? Because if I have got a low strength material and I've got a high strength material, can I make pressure vessel out of both? Right?
So it is as per requirement, that's all. What is the.
No, I have got two options. 516 is grade 60, 516 is grade 70. I can use any of them. Okay? That you will say okay. Yeah. Then what's the so what will be the difference if I make the vessel of 60 or I make the vessel of 70? Same diameter, same pressure, same temperature. What's the difference?
Tensile strength, 60,000
Resulting in what?
Thickness.
Thickness.
Small thickness.
Higher thickness.
Wall thickness.
Yes.
So because my stress is, I mean, the strength is lower. Let's use the word strength now. The strength is lower. Therefore, I must give higher thickness so that the stress is same. Right? Load per unit area, the stress is same. So this doesn't matter. Strength of the vessel, I have to only use thicker or a thinner. The allowable stress for that material is fixed. Whether it is 100, the allowable stress will be same, and I will use it for my design. Strength. You mentioned ductility. Where does it come? In the calculation, I'm asking. Where does ductility come? Nowhere. Similarly, when you're doing nut bolt calculation, if you have done flange calculation, no calculation for nut, but it works, so it's okay. So what I'm saying is that to select a pressure vessel steel, the criterion apart from strength is for economical consideration, but for safety, I want ductility because sometimes things go wrong. They have seen them happening. Stainless steel vessels, suddenly there was an explosive mixture created inside because of fault of the operator. The whole thing bulged out like that, but it didn't burst. Otherwise, they would have been a catastrophic problem. We want that bulging to happen to give me warning if I want to shut down the plant or what I want to do is. Therefore, the most critical is ductility. If I don't have ductility, I am inherently cautious. I have to be careful. Cast iron vessels, they are there in code. You know that. Cast iron. Safety factor is 10. So if I need 1 inch of that, I need 10-inch cast iron. Only for safety, because there's no ductility in cast iron. Okay, so annealed material would have lowest hardness, lowest strength, maximum ductility. I would love to use this material everywhere, but it won't be economical. So as engineers, we have to always trade off something here and take some benefit there. And therefore, we'll move on to the firstly, let me see what let me tell you this. This was the A3 line, 30 to 50 degrees centigrade above, just to be sure that the whole material has got reached there. Now we are talking about solid material that is being heated. So you heat it, it's having, depending upon its carbon content or whatever it is, it hits this line at a certain temperature, you cross it by 30 or 50 degrees, and then you cool it slowly and you will get your equilibrium structure. Nice soft structure, but it is, you say, no, I want something stronger. Then we go for normalizing. Again, we are going to heat the steel at temperature 40 to 50 degrees C above A3, hold the temperature for a short time, and subsequent cooling in air. That's the difference now. The furnace cooling is the slowest, air cooling faster, because you can get the heat. Yeah. Earlier, the word used to be still air. Now there's no such thing as still air. But what he means is that you don't put a blast of air. If you put a blast of air, then it becomes accelerated cooling, which is a term in the code, accelerated cooling. Some materials can harden excessively just by air blast. This may not, carbon steel may not, but it makes a difference. Normalized material would have higher hardness, higher strength, good toughness, and good ductility. Some normalized materials become too hard. Then what we do? We temper it a little. So we balance. Everything is about balance. Even if you do quench and temper, your quenching is too hard, it is useless because it is very strong, but no ductility. So I will quench and I will temper so that I reduce my hardness and strength but get my ductility because my bottom line is ductility. So same thing, we reach up to here 40, 50 degrees above your AC line and go down in a bit faster way. So we get what we call this changes. The perlite becomes what we call fine perlite, and that is called coarse perlite. I've got pictures of perlite. I'll show. This is perlite. So this lamellae, ferrite and cementite lamellae, this is a perlite grain, this is a ferrite grain. So this, you see spacing here, that becomes finer and finer. According to that spacing, the properties get different, improved from toughness point of view. So that is the why we want a fine perlite rather than a coarse perlite. So then hardening, heating the steel again 30 to 50 above this and quenching by dipping in water, oil or molten salt baths, because this is all now by calculation. The metallurgist knows, I mean, he has a target. I want this property. This property will come by this microstructure. To get this microstructure, I must cool at what rate? Whether it is water, it may be salt water, brine, it may be fresh water, it may be oil or salt baths, depending upon that. Nut boats, they do in salt baths most of the time. So depending upon that calculation of his, he will select the proper quenching medium temperature and he will do the job. Hardened steel is in a stressed condition, very brittle, so that it cannot be employed for practical purposes. After hardening, steel must be tempered to reduce the brittleness, relieve internal stresses caused by hardening, and to obtain predetermined mechanical properties. So it's all part of a plan. And these are your what we call continuous cooling and isothermal cooling diagram. This diagram, as against the equilibrium diagram, now we are talking of going from 800, 900, and this is time. So depending upon my cooling curve, which goes like this, I will get this phase or this phase or this phase. All by calculation, and this is a curve for every material, the curves have been determined. So he has to, based on the material and the alloy content, he will get this and then he will say, okay, I want this chemistry, I want this phase structure, I'm going to cool at that rate, so I will select this bath for doing it. And this is your martensitic structure. It's supposed to be a needle-like structure. That's called martensite. A metallurgist will assume this by seeing the morphology, but he will also do a hardness check to confirm that yes, what I think is martensite is actually martensite because the hardness is known of martensite. Tempering, process of heating a previously hardened or normalized steel to a temperature below A1. So far we were above A3. Now we are below A1 and the A1 temperature is how much? 727. 723.
Yes.
Yeah. So we are going below 723 and cooled at a suitable rate primarily to increase ductility and toughness. PWHT after welding is essentially a tempering process. So now we are here. We were at room temperature, we raised it and we cooled it. There is no transformation. We are not going into austenite. So it is only getting softer by rearrangement of locations of the atoms. Because what is stress? When two atoms are out of the equilibrium position, that is stress. So the atoms are allowed to move in the high temperature, reasonably high temperature, so that they realign themselves in equilibrium position. Thereby the stresses are reduced. And everything, hardness, everything can go down, but there is no change into austenite and reverse. That's not happening. If you go too high to this, the material will get softer. Even though the code allows you post-well heat treatment, what does it say? Carbon steel post-well heat treatment. Temperature,
95,
minimum.
96 to 620. 90. No, no, 95 carbon steel.
721.
Minimum. Maximum.
620.
Or
610 to 640.
Huh? What is it? Minimum.
Minimum.
So I can go up to 720 also. There'll be nothing left for the material. And this is happening because why would I go up to that? See, I would ideally do 595. It costs me more money enough to go higher and higher. Why should I go higher than necessary? But if I am having one carbon steel, one alloy steel, and I made a joint, and the whole assembly has to be heat treated, I have to go by the alloy steel temperature, which may be 650. So carbon steel will get now heat treated at 650, which is not violating code. But the strength has gone, which no one wants to realize. So there should be an upper limit, or you check with a sample. Now you go to ASME section division 1, except for P number 1, group 1 and 2, you should do simulation. So P1, group 1, 2 don't require. So even if it has gone to 700 and I cooled it, I don't care what strength it has because the code says you don't have to check. But that you have to understand. So effective heat treatment below A1 temperature reduces stresses and restores material properties after cold forming. You know that cold forming is detrimental in the sense I have plastically formed head what I'm making, distant, right? What is the distant? What is the shape of the distant? Hemispherical. So ellipsoidal 2:1. Can you explain what it is? What is it? How do I get the shape? That's what I'm asking. बोलने को हम बोल देते हैं. How do I get the shape 2:1? How do I get a spherical shape?
That's per layout.
And layout, someone made the layout. Now, how did you make the layout? You have to check the layout, no? As inspector.
Yeah.
Is the layout correct? He'll show you anything and say, as per layout, he will put your receipt. So, spherical shape, what is it? That is easy. That is easy. Spherical.
Calculation for knuckle.
Calculation mein mat jao. We are not doing a design class here. What is the spherical head? Can you sketch a head for me? What? How many pressure vessels have you inspected? This is rubber good or what is rubber or not? Okay. Okay. Now tell me how I should define it to call it spherical. I could as well say is elliptical. What are you looking for? Dimension names, okay. Not just
Knuckle radius.
Okay. So I want a knuckle and I want a radius. Okay.
Straight line 50 mm.
Yeah, straight line 50 mm. And what else?
Crown radius.
Crown radius. Yes. Right. So I've got a crown radius height. That will come. That will come. There's a calculation for it. So I've got a crown radius which is having a common tangent over here. There is no sharp and it's merging into the knuckle radius, right?
Yes.
Now the actual head is from here. That's why I've shown this line. This is a integral skirt for attachment. The actual head starts from here. Okay. Now I say, but I wanted the elliptical head, ellipsoidal. Now what? Now what? Now all this goes or no? What does your drawing say?
So ellipsoidal is 1/4 of the height is 1/4 of internal diameter.
Correct. For a 2:1.
Yeah, for 2:1.
Correct. So again, we are here on the diameter. Okay. This will take care of your straight length. And 1/4 of this is over here.
Yeah.
So I will join this and I will join this, and that's my elliptical head, right?
Yeah.
Right? Yes? Is elliptical head?
No, no.
Yes, yes, the word. Yes, yes. Huh?
Yes.
This is 1/4 of the whatever dia. What you
Diameter,
told me. I'm giving that much height, and this is your dia, and that's 1/4 of dia. So is it elliptical head?
Okay.
Then what is it? What is elliptical head? School, I'm talking school level. Please note, I went to school 70 years ago. Y'all are still recent. Still, I remember the formula. There's a formula, no? Ellipse formula.
Ellipse.
Huh?
What?
Correct. Correct. Thank you. So this is going to follow this equation. Correct. So it doesn't have a knuckle and a crown radius. It is a curve that follows this equation, and it looks something like this, whatever it looks like now. It is normally deeper than this one. And thickness, if you compare with shell thickness, if shell thickness is 100, this thickness also required will be 100 almost. If you go for torus spherical, it will become 130 or something like that. Thickness will keeps increasing for torus spherical head. So this is your ellipsoidal head. Now we started with from where we go to where. We have started from a flat plate, no? Forming. So you have done plastic deformation. So your ductility, which is the most important thing that you wanted in the pressure vessel steel, I have now spoiled it by already deforming the material. So that much ductility is gone. Now what shall I do to restore ductility?
PWST.
Heat treatment. The code is not insisting on normalizing. That client insists. Yeah. But what we need to do is to make sure that there is a heat treatment which restores the damage what you have done by forming. It happens in the shell also. Same thing. But the amount of damage is much less than in the head because it is two direction. There you're going, one side is straight, one side you are turning, making a cylinder. Here you are turning this way and that way, both ways. So it becomes a more critical and everyone thinks only head. No one really calculates that the shell also may have exceeded and has got this one damaged. Okay. So reduce stresses and restore material properties after cold forming. If you do in a hot condition, then it has got taken care of. In the normalizing range, if I do the forming, then nothing to be done. But when I'm doing it cold, means anything below 723 is cold. Reduce residual stresses, temper hard zones, and diffusion of hydrogen in welding. You know what is this hydrogen in welding? What is hydrogen? Moisture, I might not moisture. What is hydrogen?
Chemical element.
Yes.
Yes.
Put in your balloons for your children birthday, no? Don't put hydrogen, put helium. Dangerous. You have read how many accidents have happened because they put hydrogen instead and it blew up. Serious matter. Make sure you put helium in the balloon, not hydrogen. Okay. So hydrogen is there in the atmosphere. It is there in water as moisture combined. But in the heat of electric arc, which we will come to subsequently, there's a lot of heat in the electric arc. You're melting steel. It must be very hot. We'll come to that soon. So water also breaks up into hydrogen and oxygen. That hydrogen goes in the material. And if it is in excess, it will cause embrittlement and cracking. So we have to call why we break the electrodes, why we do so many things. You all are doing, no? Yes. Why are you doing? We try to understand a few things, why we are doing. And these things I have explained to the person who is actually baking, and he understood and he said, you will not have problem from me again. Because I have understood why I have to take the electrode. Otherwise, we just say, do it. So you do open the furnace and you put your hand and it's cold. Oh, आज सुबह खराब हो गया, उसका एक coil नहीं जलता. अरे, so what are you doing? He doesn't care because he has to put on a switch. He has to see 2 hours and he has to switch it off. So he doesn't understand anything. To reduce hardness, increase ductility of hardened materials, that is the tempering part. This is the residual stress, diffusion of hydrogen, and restore material properties. So these all things happen. Primary among them, because code talks of post-weld heat treatment, is mostly talking about tempering of the hard zones. That's the primary thing that we are requiring. So the same again, you are going to this temperature. Sorry, this is the tempering part we are talking. So that's on this temperature, and we are realigning the atoms and reducing stresses. That also helps in distortion control. Please note, because the materials keep on microscopically trying to attain equilibrium when it is stressed material. See, remember, PWHT is not required for all vessels. So you are having those thin vessels where I don't do PWHT. They work, no? So you don't have to do it. You have to understand how that works. When I have a already high stress in the material, I am putting hydro test. I am actually making deformations, and after releasing the hydro test pressure, the stress has come down because the deformation has happened. And even in operation at high temperature, it keeps on relieving the stress. That is why welded vessel also works. I don't have to everything forcefully treatment. And this is now your stainless steel. We talked about solution annealing of stainless steel. Why do we do? This is the clean structure. Austenite, 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 whatever those tiny things are. But if the steel has got damaged, what we call sensitized, then you have all these carbide formations on the plane boundary. And those are detrimental. After, why are we having or using stainless steel? Why do I make a vessel of stainless steel? Right, is corrosive resistance is there because of how does stainless steel prevent corrosion?
Low carbon and chromium.
What is rusting? Rusting. What?
Oxidation.
So talk of your ordinary steel piece. If you keep it in the atmosphere, it will rust.
Yeah, rust.
So what is happening? Actually, what's happening? In the process of rusting, I'm asking.
Due to moisture.
Correct. It is oxidizing, and the oxidized layer is falling off. Okay. So fresh metal is coming again in contact with the moisture. Again, it is oxidizing. Again, it is falling off until finally you see nothing. You can see a hole through it. Right? They called me to inspect one tank in one of these fertilizer companies in South. They wanted me to say it's okay, okay, okay. So they called me. So I went in the tank. It's in bad shape. And at some portion, I am seeing pinhole. Daylight I'm seeing inside that tank. Yeah, it has gone. I said, show me the thickness report. Thickness 2 mm, 4 mm, 6 mm, 8 mm. I said, but I can see that there's a hole over there. No, no, there we didn't check. Where there's material, there we checked. So there's 2. I said, there is nothing over there. But can we use it for water? I said, you don't use it for anything. But that is our thinking. That because there's no material, it's called neglect karo. He didn't write 0. He neglected that area and said, where there's material, I got that. So this was for corrosion resistance. So this carbon steel, I surface phenomenon of oxidation with moisture, the oxide layer falls off, more than totally gone. In stainless steel, also oxidation. But that is chromium oxide. And for that, I must have 13% chromium minimum. Then it will form a continuous oxide film on the stainless steel, and that oxide film being transparent, you don't see it. You break that oxide film, then again you have a problem with damage of the inner material until it rebuilds itself. And it is tenacious. The oxide film does not fall off. It is tightly holding on to the stainless steel, which is why we say it has got good corrosion resistance. But the oxidation is there, only it is chromium oxide, not iron oxide. Okay, now let us complete the. What is this?
The process of similar or dissimilar.
Heating
By
metal,
applying the
like heat
vision that process of trying to similar or dissimilar metal by the application of heat.
Okay.
Which story got
Oh, let's talk about heat for the moment.
with
With heat without it, correct, agreed. So I take 2 plates of steel. I'm going by your definition with heat. I take 2 plates of steel. I put them together in the furnace and I melt them and they become 1 plate. No, not welding. They'll become 1 plate. They'll become 1 plate. No, they'll melt and become 1 piece. No.
after welding the one piece.
What?
After both are joined, no one.
Both are joined 1 piece. No. So it's welding. Yes or no?
Yes.
Yes.
Yes, one piece. Yes, one piece can make one piece.
No, is it welding or not? It is 1 piece that we know. It became one. By your definition, you gave the definition, no? Heating the 2 and. Pardon?
Sorry, sir, if I'm going to put in furnace with the 2 metal
Same or different, whatever. Yeah.
Will make the plate.
Yeah. Yeah.
Okay. But if you're welding means we have to connect 2 molecules to each other.
Molecules to bapre. And there what? There what? What is that? Molecules we have to connect, and there what is connecting? If I heat in furnace, molecules are not connecting.
We are using the electrodes to.
I know that's the source of heat. I'm now heating in a furnace. I'm not putting electrode. I'm putting it in the furnace. See, one key word you have missed. That's all. That's what I'm trying to emphasize. No, where the pressure?
Fusion.
Fusion तो होता है ना. Whether I put in furnace or electrode, fusion.
Adding the
We are adding
But there is autogenous welding also. I do without adding weld metal also. Correct, no?
We are using the consumable material. Fusion.
Yeah, so without any addition also I can join, no? By just melting.
So with controlled temperatures.
Same temperature. You tell me what temperature you want. I'll give you a furnace at controlled temperature.
Avoiding the oxidation.
One word only is lacking. One word. That word is
Joining
called.
two metal by heating.
Joining two metal by heating. In the furnace, I'm heating, no? Localized heating.
Localized heat.
I'm only melting the surfaces which are adjoining each other, the faying surface is what they call. That is to melting temperature. I can put my hand on the plate, it will be cold, far away. But that portion is gone to a melting temperature, right? So what is melting temperature of steel or iron, whatever you want to say?
Depends on
Depends on, no, iron, simple carbon steel, iron. Let's talk of iron melting temperature. Iron. Alloy will fall, but iron will not go less or more. 1539 degrees centigrade. Okay, pure iron. So this will be less, whatever, depending on alloy content. To melt this or to bring the surface of my weld metal or weld groove, I want to melt it. So I put an arc. So the arc must have some temperature. Tell me.
400 to 700.
How much? Say again.
400 to 700.
No, but the melting point is 1539, so it has to be above 1539.
More than 2000.
5,000, 10,000? Anyway, it is around 6,000 degrees centigrade. And it is not a uniform temperature. It is just some average value that is quoted. Someone will say 5,000, someone will say 6,000. But there are various zones in the arc. And at the tip of the electrode, it may be 20,000 degrees centigrade. But it's a bell-shaped arc, as you may have seen some pictures somewhere. And if you say the word is 6,000 or 5,000, then it's reasonably correct. So that 6,000 degree heat source impinging on the plate causes instantaneous melting. So the moment you strike the arc, the metal melting has taken place, electrode wire is melting, and you are making a weld. Okay. We come into that processes in due course. So a material joining process is whereby localized coalescence of metals or non-metals is produced either by heating the materials to suitable temperatures with or without application of pressure, or by application of pressure alone with or without the general description. So we are talking now and will be talking today about fusion welding, where I am going to bring the two parts to a melting temperature. Why I have to melt them to join them? Because then only atomic bonding can take place at that temperature. It won't happen if I just touch two metals together. So I have to make this metallurgical bond between the two materials, and depending upon how well I do my job, my plate will be considered as if it is one uniform plate with no faults in between. So now, by definition of welding, I said localized heating. Moment I have localized heating, you know that when a material is heated, what happens to it? Physically, I'm talking.
Moisture removed.
No, physically. Moisture doesn't moisture, surface moisture.
Warpage, warpage.
No. Warpage we will come to.
Hardness.
No.
To make the wettability.
School level, just think in school if you were and I asked you question that I am making this, eating something, what will happen to it?
Thermal effect.
Huh?
Thermal effect. Thermal effect.
What is that thermal effect? Don't use high level language. Simple. What is thermal effect? You will expand now.
Make the wettability.
Huh?
Wettability.
Thermal effect.
If you make a piece hot, it will expand.
Expand.
Right? So what is happening now? I have got a weld, two plates. I have got a weld groove. I'm putting this 6,000 degree arc on that. Is going to get hot, melting, and this is cold. So local, it has to try to expand, right? Because of the localized heating, it will get deformed. It will not be able to expand as a free plate. If it could expand as a free material, there would be no stress. But because I am restricting the expansion naturally by the colder, distant material, it will develop residual stress, and that is the cause, effect of welding. Right? Two things are there. One is effects of welding, other is defects of welding. Effects are in our hands to minimize. Effect, moment you say I am doing fusion welding by arc, it will happen. How much to control, how to control, that is for us to decide. So the thermal effect will cause residual stress, which will be causing distortion. You mentioned you will have this one. These two are interrelated because the moment I allow this to happen, this may go down. Moment I restrain this, this will go up. Now, how much to this thing, everything we have to balance so that we get our job done finally. We have to get our job done. Okay. So first, let's talk of the temperature changes in welding. This is supposed to be the welding arc, which is traversing in this direction. Now, if you were to be on the arc, moving with the arc, you will find that the temperature distribution line, isothermal lines, these are constant as compared to the moving arc. So this is called a quasi-stationary state of welding. So this whole pattern is moving from here to there along with the arc. So you will see as if this temperature is always here. Whenever I'm looking at this point, even if I'm here, this temperature is going to be same. So they're quasi-stationary state. So you can see here these lines are all bunched up. Highest temperature, lowest temperature, and here they are spread out. Right? And this is giving you some idea of the temperature. If you see now the temperature, how it is now I'm talking about these points 1, 2, 3, 4, 5, and the arc is passing by the points. I will see what at the point 1, the temperature will rise very fast and it will cool slowly. And it is the maximum because it's closest to the arc. At the point 2, it will go up lesser and cool like this. Similarly, point 3, 4, 5, until finally there will be no change at some distance from the arc. So because of this, I'm telling you this because it is not so simple to calculate residual stress or anything like that because the whole thing is so different. It's not at a fixed temperature somewhere. So I will say so much is the expansion, so much is residual stress. No, every point has got a different property. Thermal conductivity, coefficient of expansion, everything changes with temperature. So at each point of this, all the variables are different. When I'm trying to calculate this point or this point or this point, I cannot do it so easily. They have done it by computers. But then it is not an easy thing. These are all research topics. They have only been able to determine this is the easy part. I can put thermocouple and I can move the arc by the side and I can determine the points. That's the easy part. After that is the complication. Another thing to note is that when this point reaches peak temperature, this point reaches after some time, because of time of thermal conductivity. So all of them don't, I mean, this would have been a straight line like this image line. All are reaching at a different time. So that complicates the whole issue further. And this is now the metallurgical aspect. So I am coming now to the liquid state, which is the well pool. Well pool temperature, 2000 degrees centigrade, we assume. Okay. So 2000. Now we come to the solidification part. That is the portion nearest to the weld zone. This point, austenite. Okay. And hot means coarse grain. Then I come to number 2, which is just above that A3 line. I will get fine grain. Then I go to point 3, which is now partly transformed to austenite, partly it is ferrite pearlite. So it's indeterminate property, not good. And if I go at 4 and below, then it is untransformed. So that is the composition of the heat affected zone in welding. Coarse grain, fine grain, and then this mixed grain and unchanged. Up to here is the heat affected zone. You will see if you do etching, the black portion that comes in the etching, that is all the affected zone, and beyond that is unaffected material, what has gone. Yeah, but it retains the property what it was. These all properties are changing after welding, and therefore we are concerned now. And why heat affected zone? Because mostly the carbon is higher here and carbon is lower here in the weld metal. So we are always concerned if this is okay, we will take care that will be okay. So heat affected zone is at everyone's head that we must check the property of the heat affected zone. Same thing. So this is your coarse grain heat affected zone. This is the fine grain refined heat affected zone. Then the intercritical I told you, which partly transformed, and the subcritical heat affected zone and unaffected materials. These are the zones. So depending upon where your notch is located, the same thing will give you different properties. So it is most crucial, critical that you see in future from today, where is my notch being located. Some DNB, who was from DNB, he tells you 1 mm from fusion line, 2 mm from fusion line, 5 mm from fusion line. He wants all the impactors in the pipelines. I have also worked on DNB pipelines sometime in my life. Okay. And this is just a pictorial representation showing coarse grain, fine grain, intercritical, and unaffected material. Okay, another thing. You all heard of arc strike? Bad. Bad or good? Bad. What is bad about it?
We started to-
So I will tell you now why it is bad. Yes, we know it is bad. Technically, why it is bad. What is happening really? Okay, so let's understand this. What is called relative plate thickness is a function not only of the actual thickness, but also of heat input. So depending upon how much heat and how much plate thickness, I may classify it as a thin or thick plate as far as welding is concerned. Okay. You know all, if I do 40 mm thick plate, I can qualify 200. This is the basis. That now I think 40 is a thick plate. If I make it thicker and thicker, it's not going to make any difference in my property. Thin plate and thick plate will give you different property for the same heat input. So in a thick plate, what I have is a 3-dimension heat flow. Means suppose I'm just depositing welding over here. The heat is flowing in transverse, longitudinal, and through thickness. So its cooling rate is fastest, depending upon thermal conductivity of the material and all that. It will cool fastest, and there is this factor tau. It will come calculated as 0.9 by a formula. Okay. And this is the formula where you can see this tau. H is the thickness of base metal. These are the temperature differences, don't worry about them. And H is the heat input. So H and under that is H net. So if the plate thickness goes more, tau goes more. But if the heat input goes more, tau may reduce. Okay. Now I want tau 0.9, or I must calculate based on whatever the data I have over here, whether it is going to be a thick plate or a thin plate. Okay. Now, if this goes below 0.6, it is actually something like this, where this is as hot as that almost. So only two-dimensional heat flow is happening. It won't cool any faster because it's already got no third dimension. So I have inherently safer when I'm bending a thinner material because of this two-dimensional heat flow. And there's always this confusing intermediate condition where it is neither thick because the transition, you can't just jump from 0.6 to 0.9. So neither, I mean, above 0.6 but less than 0.9 is an intermediate condition, safer for you to consider it as a thick text. Then you can't go wrong. If you need, now what are we trying to do? Determine preheat, determine so many things like that when we want to. Now I know it's all manufacturer's problem, but if you can help him, it's better. He gives you more this thing, respect. Okay. Now this is a thing that no one appreciates, that even if this is thin and even if this is thin, because of this configuration of fillet, I have three heat paths. So it automatically becomes thick because I have got three heat paths. And this is the most neglected thing in the world, the fillet weld. Neither I care to qualify the welder for fillet weld, neither I care to qualify a procedure for fillet weld. Once I've done my groove weld, everything is passed. And the failures happen here. Biggest failures that have happened in the world for other reasons, structural, because of faulty fillet weld. Offshore platform, one hydrophone mount was made, the fillet weld was made, North Sea, I'm talking North Sea. Crack was there in that fillet weld. The crack went into the leg sheared, whole platform went in the sea, 300 people died. And it's not easy dying in cold of North Sea, okay? Apart from dying. So until you die is a problem. But these are the things that happen only because everybody is looking at what? Long seam, CC, most important attachment belt. I'm not going to look at it. And that is where the problem comes. T-joint. I must see the T-joint. Everyone will see it. Now T-joint, there's no problem because everyone knows everyone is seeing the T-joint. So nothing goes wrong there. Go and look at what they don't want you to see. So you see, thick plate extra part does not increase apparent visual thickness because you already had 3D transfer. So there was no problem. So now come back to the arc strike. Why is it detrimental? I'll give you a hint. This is the answer. Now you tell me.
Temperature at which the cooling rate is critical.
Temperature of the arc is fixed. Arc is happening, no? What is the arc strike? A sudden arcing. Okay. Someone has written somewhere that the duration of the arc strike is 0.2 seconds. Okay, I don't know better, so I'm telling you what I read. So what is happening? Each net is very small. So tau goes up. So no matter how thin your plate, physically thin, because this is very small, tau has crossed 0.9. So what happens now? Two things happen. One is I got a hardened structure because thick plate. I didn't do preheating or anything like that. No, I just struck the art for 0.2 seconds and I got a hardened structure there. Second, I deposited material also, which is not proper weld metal. We'll come to what is proper weld metal during the day. Okay, main thing is that I got a hard heat affected zone, and if I don't get rid of it, it can cause me problem. If it were alloy steel, it may have caused a crack. So we know the procedure, what is there for handling the arc strike.
Yes.
What is that?
Yeah,
Pardon?
MPA.
PA for what?
For
First you grind it, no? First you grind it.
First grind it and ensure the.
First you grind. And then you do your MPI, do your PT. But the correct way, the best way, which is I read in one of the low temperature piping codes, is that you should, after preparing that local surface, you should etch it. If it shows a spot of HZ, that spot should be removed. After which, if necessary, you fill up, after which you do the PT, MT, whatever. That is the ideal way. What we are doing is practical. Everyone has done it. You can say from 40 years I'm doing. What happened? I can't say anything. But at least you understand now that there is a bad weld metal which is removing by grinding, but there is also HAZ which is hard but may not have cracked. If it was cracked, I would get in MPI or PT, but it hasn't cracked, but it's still hard. So over time, it can lead to something. Okay. So what is arc strike? So now coming to the second question, is it detrimental in austenitic stainless steel also? Yes. Yes, so why? और मैं क्वेश्चन सो सिंपल ना yes no करते जाने का. I gave you the answer.
Yes, sir.
I gave the answer. I gave the answer earlier, but you're not listening. I told you two effects of arc strike. Two effects. So what's the other effect? What is the effect of arc strike? Yeah, heat at local point. And other effect, I told two things are happening, no? Heat input. I'm telling the same thing on the heat input. What was the other effect?
Chrome oxide make.
Not chrome oxide. It is not weld metal. Something has deposited.
Which is not
Not proper weld metal. Proper weld metal will happen when the process of welding stabilizes. In 0.2 second, the process of welding has not stabilized. So it is deposit of something which will affect your corrosion resistance of stainless steel. Why we want stainless steel? Firstly, I broke the oxide layer. I melted and removed it by that thing, and I put some material. I don't know what I put, and that will affect my property of corrosion. Okay. It's 11:30. We can have a tea break if the tea is ready. All those online, please go and make your own tea and come back. Yeah, I want tea coffee, of course. I need it more than you. I will inform him. Sir. Huh? I will inform him.
Sorry, Pratap.
Ah.
You have coffee there?
Coffee. Coffee. Okay, next.
आगे एक बात बताओ, ये जो बताइए
Sir, shall I call?
Whenever, no hurry.
5 minutes.
Yeah. बोलो आज हम नहीं है, बाहर है, आज नहीं होगा। आज जो भी है तो अभी सुरेश सर से ले लो, हमारे साथ तो है नहीं। गुड मॉर्निंग, क्या हो रहा है? अधिकारी नहीं हुआ? ओके, पंप डाल रहे हैं ना अंदर? ओके ओके, ठीक है। ओके, और डीजल लाने का है? किसमें? कितना क्या?
जैसे कि ना उनका फोन आया ज्यादा कॉल हो रहा है, ये उनको बात करूंगा, उनको कॉल किया
15 सौ का जाना पड़ेगा ना?
हाँ टीवी में तो पहले टीवी नॉर्मल है 2000
Okay, so we understood something of residual stress. I'll give you another explanation also. Okay, these are two fixed supports, rigid, and there's a bar which is exactly fitting in between the gap. Now, if I start heating the bar, what will happen? Expand. Start expanding.
What is there?
They can't expand.
Start bending.
Bending, if it is long, slender, if it is not long and slender, it will start plastically deforming. Okay, so it will, length will not change, its dia may go up like this. Okay. Now I allow it to cool. What will happen?
Retain its shape.
It will be cylindrical shape, not in the same dimension.
Yeah.
As it cools, see the length, this is only preventing, it is not holding. This support is only preventing movement. The length was trying to expand, it couldn't. So for volume constancy, the diameter went up, deformed. Now if I cool, the length will become shorter. It will just fall down. Okay. If I don't, if I hold it, that means I don't allow to expand, I don't allow to contract, then I will generate tensile stress in the bar. Because it is trying to contract, The support is holding it. So I'm going to generate tensile stress in the bar. This is the fundamental of residual stress in welding. Because it is held. The cooling weld metal is held on both sides by the cold metal. If it can't hold, it will crack. We are assuming the crack is not happening. So it is now under heavy tensile stress, weld metal. That's why the weld metal cracks. They do not crack. So this is a distribution of residual stress in this direction. You see the weld metal is having very high tensile stress. And as it goes out of weld metal, it has to become, because this tensile and compressive must balance. Equilibrium has to be there. So if I'm generating high tensile here, I have to generate an equivalent. So this area plus this area equal to this area. That must happen. It's not so simple as this, because of the structure may be very complicated, but net effect has to be in every structure. The stress balance somewhere tensile must be balanced by compression. Otherwise, the structure will fly off somewhere. No, it cannot have a stress which is not unbalanced. And if you take along the length of the weld, the central part is in tension, must be balanced by compression. So the two ends become in compression and central part is in tension. Now these, if the plates are very thin, they are manifest as distortion. If the plate is very thick, you will not see the distortion, which is there always, but you will not be able to visibly see a movement. So now it is trying to pull in. So you will have this sort of thing happening in thin plate only. You can see it. This will cause transverse shrinkage. So this one will start getting shorter. Like the bar I told you, it got shorter. Here I heated this portion, I didn't allow to expand. Now it is cooling, so it is pulling everything in. So your thumb rule is that whatever is the root gap 3 mm, that much will become shorter in your this one. Whether it's a circumference, whether it's a plate, the root gap is equal to the amount of contraction. So your okay. Then you have angular change. Why should I get angular change?
Due to thickness, heat input.
Thickness, input is said for.
Due to smaller thickness.
To do welding of two plates, what do I do? I have given you two plates. Now you give me step-by-step instruction what to do so that I can weld them together. Tell me.
We have to put the clamp for to avoid the distortion. And we'll do the control welding.
That is fast. You're going too fast. So no computer programming. You know, learn computer program. He'll teach you step by step. Computer is stupid fellow. Unless you tell each and every step, it will only say do the welding. Computer cannot do welding. I give you two plates. First you must make edge preparation. Okay. So what's the edge preparation I'm doing?
Angle.
What angle? What
Bevel
angle?
angle, bevel angle.
What is the angle? I know bevel angle. What is the angle?
32
Degree.
30 to 35 degrees.
35.
110 bevel.
Any reason I should take 30 or 35 or anything like that? And from where you got this 30, 35? I'm not going. Okay, so now I have two plates. This is one plate. This is another plate. Can I weld it?
No.
So what do I need to do?
Edge preparation.
So what shall I do? 35, 40, whatever you are talking, I don't know. Tell me. I will bevel it.
Yes.
I'll keep a root face. I'll keep some root gap. I will bevel it. Okay. You were talking of an included angle. How much?
70 to 70 degrees.
70 to 7.
60 for why? I need a bigger angle for GTA, smaller for SMA. So remember one thing, why I showed you this figure first. Ideally, this is how I want to weld it. Right? I can do it also by submerged arc welding.
Yeah.
If it is within 16 mm thick. I do one heavy pass from here, then I turn it around and do one pass from there, two pass welding. I can do, but not easy. Not easy in production. It's okay in the laboratory. I did it very well in the laboratory. When it went in the jaws, I made big mess. So never mind. So now what are we doing? We are removing from this metal good material, sound material to make this V groove, to fill it with weld metal of doubtful quality. Until we have done the WPS, PQR and the NDT, we don't know how good or bad the welding is. So I want to keep it minimum, right? So why was you were 60 to 70? Why not 50 to 60? Correct. I'm worried about something called lack of fusion, which is a defect which I cannot find out by RT, right?
Yeah, we can find out.
The planar defect. Don't get in RT, you get by UT. And so many jobs are going with RT with the lack of fusion, but they're working, fortunately. But it's an inherent fault of the RT process, not the fault of the operator or any procedure. It's a limitation of the process. So ideally, welding should be done by a combination of RT and UT, but nobody's listening to me. They say, do this, do PIUT, do what you like, somehow you get the job done. Okay. So anyway, so I'm removing good metal, good material, filling it with weld metal. I'm keeping a certain angle so that I can get a good fusion. Right? If I do my job properly, I keep 75 for GTA because there is a nozzle.
Yeah.
Here I've got only a 3 mm, 4 mm electrode to manipulate. There I have to manipulate the whole nozzle. Therefore, I need a bigger angle, or I can go for a compound angle. Something like that. Compound angles are also there. It is bigger in the bottom and then less narrow in the top and so on. Yeah, it is only commercial. It is my, I want to finish my job faster. Ideally, I want to do this, but I can't. So I am trying my best to do. So now what am I doing? I am welding this 60-degree, forget about 60 or 75. I am welding a V where I have got one bead over here, I have got two over here, three over here, four over here, right? So shrinkage something here, shrinkage more here, shrinkage more here, shrinkage more here. So what's the net effect?
Distortion.
Angular. Because of my V group. Yes. I can minimize it. What I'll say, I will take a double V. I will start welding something over here, then weld something over here, then weld something here, then weld something there. Finally, I will manage to get it reasonably correct. It won't be perfect ever, but it will be within acceptable limit. Yeah. So that is what is happening over here. If we are having a single V, the angular change will happen in a fillet weld because there is shrinkage now here. Remember that. So this is going to pull. See, weld metal is going to either deform or it will pull the plate, nothing else. If it can't, it will crack. You can't say, oh, nothing will happen. It will crack or it will pull. So that plates, these are called thinner plates. It is very obvious how the deformation will happen. How to correct it also some little bit. There is
But distortion is only because of heat, no?
primarily because of contraction and expansion, differential contraction expansion. If I take a plate of or a piece of steel, freestanding plate piece, I heat it to 100, 200, 500, it will expand freely. I remove the heat source, it will contract back exactly where it was. No stress, no deformation, no nothing. Moment I start putting restraint, then all these problems will come. This you may have seen as I'm welding, the gap closes because of contraction. Now it's a function of how much heat input versus travel speed. And if it is in a high, this thing, you see, this is in shielded metal arc weld. If you have got very high heat input, it may actually increase, which we rarely see. But mostly it is, we see the gap band ho gaya. So my penetration is gone and my I have big problem. But this can happen. And mostly we are putting tack weld and holding it, but if the tack is not strong enough, it cracks because of the stress being caused as the weld metal is being made. So you can have cracked tack. So you have to have your tacking design. How many tacks and what is the thickness? It may be a multi-pass tack, need not necessarily only be one root run in the tack. If the structure is very thick and heavy, you may need to put a sufficient amount of weld metal, call it a tack. And the tack weld has not been defined in any code till today, and they are trying from 20 years, section 9, to make a definition of tack weld, but there is no definition. So whatever you understand, you understand. Then these are just effects of welding deformations, as you see when you're trying to weld this piece, which is before welding. When it is heat in the hot condition, it is going to try and expand, so this length has to increase. So it will cause the deformation, but there is also resistance. So when it starts cooling, it will finally end up like this because it's not free. Now I have got a shorter length here and a larger length there. To minimize the effect, you preset. So before that, instead of getting the V, you make the reverse V before you start welding and hope that by the end of the welding, it has become parallel. Same with that weld. You slightly incline and make it after welding it. Finally, I want the welded structure to be correct. What I set up, what I do is all a means of ensuring that it will be correct. But if someone goes and rejects your fit up because it is bad, you tell him, okay, when it is done, it will be okay, then what's your problem? Like there is a pipe being laid, cross country, or whatever you call piping. I'm supposed to see every fit up. The contractor is down shouting at me that you passed my fit up, passed my fit up, passed my fit up. It's okay. I say, no, the gap is too big, something is not okay, something not okay. And the thing does not have full RT. Then it becomes critical because I don't know in the end what's the result. So I tell him, okay, if you give me additional RT of this joint, I will accept. He's also happy. I'm also happy. Finally, I want my net result to be correct. These are means, but we should not blindly say that because you told 1.5 mm gap and it's 2 mm gap, therefore I will reject it. Easy for us to reject as inspectors. But pain of correcting for that little bit is not worth the trouble. Again, presetting. So he has put a clamp here and he has bent it like this in the other direction. He had to do the welding and I release the clamp and I hope it becomes straight. Now we come to discontinuities of welding. All welds are discontinuities, right? It's just that when this discontinuity increases to a level where it cannot be accepted, then it's called a defect. Defects are not accepted. Finished. Discontinuities are there. Even if they are not detected, they are there. It's just our luck when we do our RT or UT or PT that we found a favorably oriented discontinuity that we could detect it. Otherwise, it may be there, it's okay. We don't lose sleep over it. What we have to ensure that the procedure was made right, the processing was correct. Do you go and check the dark room ever of the contractor or anything? Do you check?
Yes.
What do you check?
Uh, Somewhere is a light leakage.
Yes, always there's light leakage. So mostly the AC is not working the daytime, it works only in the night time. He doesn't have a proper safe light. He puts a bulb and he puts some tape on it and say that is my safe light. And these are the dark rooms we see. What quality can you get? You'll miss the fine defect. See, the obvious big defect, no one's going to miss that we know. But it's the fine ones that we are talking about, where it matters that how correctly was my processing done. The fellows are there, he looks at me and says, all kala karne ka hai kya? I will put more and do something. If it's too kala, I'll put potassium permanganate and remove the kala. That's foolishness. You are defeating the purpose of the process. First, I go and check, do you have potassium permanganate or whatever you are talking about? Is it there or not in your? If it's there, I throw him out along with that. Because I know what he's trying to do. Finally, in radiography, we are talking contrast. If I just blindly remove the densities, it will not distinguish between the defect and the non-defect. It will remove the density from the whole film. So my contrast will go. And the end of my radiograph, I mean, purpose is lost. So unacceptable discontinuities are termed defects. All defects must be repaired to conform to acceptable limits. So we don't want perfection. All we say is that if my slag permitted is 19 mm and I've got 25 mm, all I need to is to bring the slag to 19. I don't need to remove the whole slag. How we do it? When you see, we say, "Oh, nikal do pura." But by code, so long I bring it down to 19, which is an acceptable limit for my case, then I say it's okay. There is a typical case that came once when we had to do RT before PWHT and RT after PWHT. Client wants all those. Okay. So we did the RT before PWHT and we got 19 mm slag. Okay, acceptable for the thickness. Then we did RT after PWHT. It became 21. How? How?
It will expand.
It will expand when it is heated, so it will contract when it's cool, no? Or it will keep expanding only.
It's a defect because
Now my job is 100 mm thick, okay? In the radiography, I don't know which side it is, whether it's near this surface or that surface, because I have to find by some other means, which is possible. Now, if I say that I did it before PWST and it was 19, I don't want to, I cannot reject it because it is 19. Is 19 is acceptable? Now it's showing 22. How is it showing 21 is my question to you.
Due to wrong technique.
Wrong means kya? What is wrong about the same procedure, same operator, same company, same everything, apart way doing the NDT? See, I can easily say as an inspector rejected. The easiest part of my life. No, not acceptable. You can do what you like. Go and dig out 100 mm or 50 mm of material, weld it, and all that rubbish you can do. And I will just sit back and take a holiday until it's done. That is okay. But that doesn't help unless you understand what has happened. So you have to tell me what went wrong to make it appear unacceptable. Okay. Now to do that, you have to understand that when I do RT, what am I doing? This is my weld, this is my film, and this is my source. It's all along the length, right? So I expose it, I keep it over here and expose it and I get, and I got this 19 mm slag. Okay. And this was a circular piece and all that, so okay, more complicated. Now this everything is manual. Keeps it in a place thinking that it is centered over the defect, right? So now if I look in this view of the weld metal, this was my defect. Okay. And I put my it so happened that my source was directly on top of the defect. It will show minimal. Next time when I put it, if my source instead of being directly here got shifted over here, it's elongated. It got elongated. So once you understand that, then you can say, okay, now on record, I still can't say it is 20, please note. I will get hauled up by an auditor. So I have to say it's 19, but I know it is 19. Neither do I want to encourage the operator to do it again. Because then each time he gets a defect, he will do it again. And I'll be the cause of giving him the idea. Better to accept 20 mm, knowing it is 19, than to tell him to go and do something which is totally wrong. Because I told you it is chance, matter of chance that this happened to be on top of it. If it had been here in the first place, I would have got 20. I would have repaired it anyway. It happened so to be right on top of the defect. So those are the things that easy to repair the defect. I mean, easy to say repair the defect, but very difficult to repair the defect. So now the defects come due to faults in design, process, and metallurgical, right? So defects of design. What would you suggest? What are the defects of design? How can design cause defects in welding? Groove design. So I put the wrong groove. Once I put the wrong groove, my lack of fusion is ensured. So I can have design related defect. Process are the common ones. Everything is due to process. And when I say metallurgical, then it is the crack type of thing. Those are the metallurgical type of defects. So design related discontinuities include problems with design or structural details, wrong type of weld joint for application, or undesirable change in cross section. So thick, thin, I'm going to weld without proper thinking. Welding process related are discontinuity resulting from the process, including undercut, porosities, slag, intrusions, overlap, tungsten, lack of fusion, lack of penetration, craters, melt through, and underfill. We'll see some examples of these as we. And the metallurgical are arc strikes, cracks, fissures, fissure. Fissure is a hydrogen-related defect actually. Segregation and lamellar tearing. Do you know what is this lamellar tearing? This is lamination.
Lamination.
No, lamination in the plate is different. Lamellar tearing is something that was not there, but it has happened due to welding. Lamination was there. I can find by UT. And it's a mid thickness mostly. Lamellar tearing is something that happens near to the weld zone.
Yes.
That's it. Again? Near it. Is typically it will happen in this type of joint. T-joints. Now what, as I told you, now we have got high tensile in the weld metal. So it is giving high tensile in the through thickness direction of the plate. And if the plate is not able to withstand the stress in the through thickness, which is never tested normally, unless it is required specially for offshore application or something, then you will do through thickness tester. Otherwise, this is not through thickness tested plate. So if it has some impurities, inclusions, or some weakness, which is you can't detect by NDT a weakness. It will only show after welding. Then you get a step like cracking over here. And that is a lamellar tear. If it's not detected, then this piece can fly off ultimately when those steps
So this crack is in base plate, right?
in the split outside of the weld. Okay. Now this is just someone's thinking that occurrence of weld discontinuities as per the process. In SMAW, someone has done an analysis and found that the most common discontinuities are slag inclusions, porosity, lack of penetration, lack of fusion, and undercuts. In submerged arc welding, there may be lack of fusion, lack of penetration, slag, and porosity. In gas metal arc welding, porosity is very common, lack of penetration and lack of fusion. And in GTA welding, porosity and tungsten inclusion. There is somebody's analysis. It may vary from different manufacturer to manufacturer depending upon how careful he is about this particular thing, porosity, whether you have proper gas coverage, whether your gas is proper or not. We have had problems with gas. Nominally, it's argon. That is on paper. What is inside the cylinder? You don't know. So we had the problem, the site welding and the whole arc was going crazy. So, okay, what has gone wrong? Is the machine not okay? What has happened? Suddenly, everything is going okay. Change the cylinder. Again, same thing happening. Change the cylinder. Again, how? 3 cylinders were defective at one go. 4th cylinder, suddenly everything became okay. Until then, you can't understand because you think one cylinder is bad, next one must be okay. 3 cylinders came bad because what? They got contaminated. How does cylinder get contaminated? If you exhaust it. Totally. Okay, when you purchase commercial argon, the process, see, liquid argon is 99.99999% pure, liquid argon. The contamination occurs in the filling process. So my cylinder, suppose is empty and full of air, whatever will be there. Okay. In a commercial quality argon filling, he will make it vacuum once, purge it once, and then fill. So whatever contaminants got out by one vacuum and one purging, rest are there. So you'll end up in a problem. If you want high purity argon, then 3 times he will make vacuum and purge, and then you will get 99.99 whatever % argon. Okay. If you have got that good purity argon and you retain a small pressure in the end, don't exhaust it completely, then you will get a good quality. Good afternoon.
Very good afternoon and welcome, doctor.
I thought you're not coming today.
No, how can I not? Our, I was, I'm saying
Where you? At 10 o'clock in the morning.
today, I was doing my residence, but on a call actually today, which normally doesn't happen. But today is actually a holiday.
Let's go.
So, I mean, Dr. Saab is our guru, and all what I have known is only 10% what is he has given us. So it's up to us to extract that additional 90%. So doctor will be with us doing the courses regularly. And thanks for coming on a Saturday. I hope that you are getting the benefit. Please ask him as many questions. It's basically to upgrade us. Yes. Right. Thank you, doctor, for coming in. I'll not disturb any further. We break at 12:45 for lunch. We'll just walk down in the past next building.
Okay.
Yes, sir. Okay, doctor.
Okay.
Anything?
No. So I forgot what I was saying. What did I say? Argon purity. Argon purity. So if you maintain that positive pressure not saying 15 psi or 5 psi, anything that prevents air to get in. You will maintain the purity of the argon. And because your cylinders, if they are your own, I'm talking about manufacturer, of course, then you can get refilling done and get the good purity. But if you're just replacing cylinders with somebody else's cylinders, then you will always land up with a problem. Then you get all the porosity and you get worse things than porosity also because the arc became unstable. We could not do the welding. Forget about the porosity. It didn't happen. Okay, now this is an interesting subject of effect of repairs because that's what I want to tell you about not going blindly for repairing. Welds are repaired to eliminate harmful defects. However, although weld repair may qualify a weld to a workmanship criterion, means slab is become 19, whatever it is, it does not necessarily ensure an improvement in the structural reliability of the weldment. Working conditions under which a repair is made are usually not conducive to good workmanship. Restraint is inherently greater, increasing the probability of cracking. Chances of creating new discontinuities, particularly metallurgical ones, are increased. The harmful effects of an unsatisfactory weld repair may include increase in local residual stress. May not be distortion, but definitely the stress will be up. Introduction of new discontinuities not detectable by conventional NDE, degradation of microstructure and fracture toughness, grain growth, carbide precipitation in stainless steel, hydrogen embrittlement, thermal straining and sensitization, aggravation or extension of pre-existing discontinuities that were undetected during origin. So it is not the best thing to just, when you have a doubt, obvious things obviously have to be repaired. There is no question. But when I'm having that 1920 problem and I want to see what to do, then I would like to be aware of what damage I'm doing. Now, you all know that when we are doing welding with impact, we have to heat input, limit heat input. So now what did you do? You have got a permitted heat input. You are within that heat input and you did the welding. So far, so good. Now you have got a repair. Again, in the same spot, I'm going to put double the heat input. Who has taken care? Sometimes clients ask for procedure to be tested after repairing and rewelding for this reason. Now you can say all clients don't ask. So how is it working? Ideally, the repair is a small percentage of the totality. So if this has got weak or whatever you can say, the impact properties has gone down, it is local. The bulk of the material is still what it was, which is why we are surviving and saved. But if you check at that point, you may have lost your impact toughness or whatever property you want. Therefore, doing this is a very good idea, but maybe unnecessarily creating a lot of expense. But it's only a test piece, remember. So you get the confidence that even one repair, if I do, my toughness is still not compromised. Because suppose there's no limit to how much repair I can do in a job. Sometimes he says cut and reweld the seam. You may have told, very bad, cut and reweld the seam. Then what have you done? I have finished the whole thing. Otherwise, the solution to that is again remove that 5-10 millimeter from each, so that that heat affected zone is gone when you're making the new seam, if you can tolerate the dimensional change. But then you are more sure of the property of what you have made.
Depending upon material, on the times of repair is allowed.
Yes.
Thermoplastic material.
Thermo?
Depending upon the material you are using,
No, we are talking
number
about
of repairs,
no,
2 times repairs only allowed.
then कहाँ लिखा है?
Depending upon client specification.
Client specification. Huh? So he has got some basis, no? The basis is here. I have exhausted my damage due to heat input in the first go. Or okay, you qualify a procedure with double heat input and use half heat input, no problem. But nobody does that. So whatever is the heat input, he measures by the current, voltage, travel speed. He's saying that is my permissible heat input. I have proved it. Even though my properties are on the higher side, but I have only proved that. Moment I do double heat input, I don't know. Now, if I re-weld with that in a test piece, then I'm satisfied.
Sometimes we have the repair procedure also.
Yes, but what do you write repair procedure? Gouge out, re-weld, do PT, use WPS, so and so, and put it back. Does the repair procedure say that do the double heat input and check the impact toughness of HSI? No? Repair procedures we have seen enough. Look what it says. Gouge out, do PT and put the weld back.
For LAS material also,
Huh?
we, for LAS, low adult steel also, sir, we have some restriction for the repair.
Yeah, for this reason, no. For this reason. If you're have you welded quench tempered steel? Quench tempered steel are those which are having very good strength. By the quenching process, I got hard structure, then I tempered it and I made it ductile, but with still good strength. Now the strength came from the structure. Remember, the microstructure gave the strength. And when I'm doing welding, where is the quenching and tempering? I'm not going to quench and temper my job. So this is going to be as welded. If it's a structure, we don't even do PWHT. We only do as welded. So my martensite, whatever structure I got tempered, martensite, everything like that, has now become ferrite and polyite. Or maybe something better than that, depending upon the material. And if it is too much heat input has been given, it will fail your impact is the first thing to fail. And in that I saw Japanese steels are very good. They can tolerate abuse. German steel came in our yard, failed immediately.
Oh.
Impact. If you give excess heat input, the quench tempered structure is lost. No, anyway it is lost. But the Japanese steel could withstand that. German steel could not withstand. So in fact it failed. Okay, now some examples of common weld discontinuities. What is this? Acceptable, unacceptable. How much acceptable, how to accept. As I said, my aim is not to repair, but I must be satisfied that I am not accepting something incorrectly. Can I accept it? If I can accept, under what condition can I accept it?
Won't be to thickness.
This thickness. Yes, you are right. So I must, that this amount of metal from here to here is greater or equal to this. Correct. And obviously it's a sattvic, it's not a lack of fusion or anything like that. Now, how do I determine that this is okay? I may not be accessible to me, no? That joint to measure. So how do I assess that this metal is adequate, equal to or more than that?
So we need to compare with the design parameters,
No.
the governing thickness.
Yes, but how to measure the governing thickness? It's not accessible. Your wedge is not accessible by hand, I mean, or crawling through somewhere in a pipe, small pipe. RT,
No, no, it's not thinking.
only RT.
Which is the thickness.
Density of the film here should be equal or less than the density of the film outside the weld. It means that the thickness is equal or greater than the base metal thickness. Simple. And no sharp, of course, that one you have to take care. There is a cross section, you can see it, but in the weld you have to make out that there is no lack of fusion or penetration like that, and it is a proper suck back. That's it. What is this?
Excess penetration.
Very obvious. Now, what's wrong with that? Why have I put it as a discontinuity or whatever you call it?
This is for process flow.
Yeah.
This will affect the flow of
If it's
the.
a small diameter pipe, it will affect the flow. And if it's not so small diameter, if it's a 60-foot vessel,
Damage
diameter,
the welding.
huh? Pardon?
The flow will be damaged.
Damage the welding.
Restricted and,
No, this is not a pipe now anymore. Pipe, I agree. I've got a half-inch pipe, I'll block the whole pipe only with the excess penetration. Now I've got a large diameter tank, 20-meter diameter tank. And I got the same type of weld. Now what? Now what's the problem? No more flow problem. It's a storage tank. Now,
These are more heat input.
forget the reason.
There is an acceptance criteria for excess penetration also in 1104, sir.
Correct. So why is there a limit on excess penetration is the question.
Okay.
It's a limit, agreed. For the
So, it may causes disturbance while we are gauging or while we are producing some product inside of it because of this excess penetration.
there will be stress concentration,
Yes, sir.
sudden change in section.
Yes.
So this becomes a high stress point because of that. Okay, now I say, again going by code words I'm talking. So I'm allowed 3 mm or 1.5, whatever, 2 mm excess penetration. Okay, so I cut this off like that and I say it's 2 mm. Now will you accept? My code is acceptable, but it's not acceptable. The idea behind having the limit on this was basically the slope of this line, not just cutting off like this, not just cutting off like this. The stress concentration is reduced only when the slope decreases, not when the total height decreases. So it is not, everything can't be written in code, but you have to understand that I want a limit in the excess material so that I get a slope, and some British standards, they define the slope. This ASME code does not define a slope. It just says that you make a limit to the excess penetration, reinforcement. But the idea is to have a gradual transition of shape. After all, see, ideally, when I'm doing welding, I want so much weld only. All this is of no use in anything, nor is anything here. I just want exactly to fill up the thickness, period. But if I try to do that, I will invariably end up with underflushing. Therefore, I have to say, okay, by reinforcement dialog to make sure that I have at least so much weld material. That is the only reason. But it gives me no credit. In fact, it is a detriment in some cases. And that's what we are talking about. I tried to fill up exactly the amount and I landed up thinking that unacceptable. I have to go and fill up. Now, what is it is better. So what's wrong with it? What about it?
This is cosmetic defects.
Cosmetic defect. Yeah, only cosmetic. How do I remove spatter?
Effect in the electrode.
Pardon?
Lack of fusion, sir.
Lack of?
Fusion.
No, that is, but it's outside the weld, no? Yes, hot particles. I'll be showing you videos of the metal transfer in GMA, and you'll see spatter particles running about. So this, while welding, the particle has been ejected from the weld metal and it has fallen over here, and it's lightly adhering. It may not be fused really to this. Okay, it is adhering, it's there. How to remove it?
By chipping.
Best way. By chipping. Grinding is not the best way because you may not be removing, you may be only pressing it in the surface and thinking it's gone, but it has not gone. And why don't I want this? For two reasons. One is that under it, there is a crevice. So depending upon material, depending upon whether this is the inside or outside of the weld, I will get a proper possibility of crevice corrosion inside. Stainless steel, all those things like that. Second, am I going to accept, suppose I cleaned up all this. Am I accepting this weld? Yes. Why did this pattern happen? Why does it happen? It's not normal, no?
Due to current, due to
Improper settings, right? So when I did my WPS PQR test piece, it was very nice because 10 people were looking at the welder. What are you doing? He was very careful. So I got, yes, some occasions pattern will always come, but not like this. This is clearly indication that there is a wrong parameter setting. Therefore, my whole weld now is in question. I do not accept the weld at all. Because it's telling me that you've done it wrong. And just removing cosmetically, as you said, to make it look good, doesn't prove that it is good. I'll say cut and rebuild. Once you do it, they'll be careful. Until you keep accepting, they will give you. They will give you how much you accept. This center line crack in submerged arc weld metal, it happens if the depth of this thing is more than 2 times of the width, then the center line cracking can happen because all the impurities will solidify in the last in the end, and due to tensile stress, it will crack. This
lack of vision.
lack of side wall and incompletely filled. And you will detect it with the X-ray. Yes or no?
Yes.
You won't.
You
But who does? Because I have done X-ray. I don't care. I won't do UT. This
lack of fusion.
at the root. In fact, the root two pass weld, and this got infused. Okay. So this wonderful method of welding, which is actually technically okay, theoretically okay, it was used on one ship. I'm talking of 40, 50 years ago, maybe before most of you were born. So that in ships in those days, they didn't do RT too much. Because what they said, the ship should float. So long as floating means I have done everything okay. So this ship tanker was made, and Cochin shipyard had this latest machine. We will do 2-pass welding, and very quickly it got made and it floated also. 20 years later, every weld had developed crack. And during the routine survey, the senior surveyor who had gone over there, he happened to see some cracks. So he took me there. I said, let's do X-ray of these joints. Every joint was like, every joint. The ship was scrapped. And the owner was very upset, obviously. After that, they told me, don't go near the ship again. Okay. This?
Flag.
This?
Porosity. Porosity is the.
What is the item?
Yeah.
Crater. So crater may have porosity, crater may have cracks which are not visible. If you want to imagine, some of the cracks are there if you want to, if you care to see. But basically, it is the fault of the stoppage. How rapidly have I withdrawn the electrode and stopped the welding? It can cause problem. Then I have to grind out and re-weld and remelt and hope that it gets. But mostly it's shallow, so it goes off most of the time. What's this?
Flag.
Where's flag?
External undercut.
Yeah. Okay, so what's a permissible undercut? So I
50
will,
mm acceptable range, sir.
pardon,
50 mm acceptable range as per 1103.
15 mm.
In length.
No, depth you are talking about. 0.8 or round it up to 1 mm, whatever it is. The code will write anything they like, so it's okay. 0.8 or 1 mm. I will accept in depth, right? Now, as per ASME code, what about the length? He's saying 50 mm as per some code. What about ASME code? And by the way, that 1 mm or 0.8 mm is not universal. There are two paragraphs in the code. One paragraph, first one says that it should not infringe on the required thickness. As an inspector, you don't know. Suppose it's a 10 mm plate. Whether the designer required 10 mm or the designer required 9 mm, I don't know. Unless I know that, I cannot accept any depth of undercut. So it should not infringe on the design thickness, number one. Number two, it should not exceed 0.8 or 1 mm. All right. Now I'm asking you number three. What length will you accept?
Acceptance criteria.
Just tell me, no, based on the ASME's code section 8, what is that? Open the book and see. I have no problem. It's all open book over here. Open. There is no criterion on length. Now, on one hand, we are talking about well discontinuities. So it's a yours a discontinuity. It's come categorized as a discontinuity. Right? Now, what am I saying? How did it happen? You must understand that. You must think. Why did it come? When I did my PQR test piece, I didn't get any undercut. So he has obviously exceeded the parameter. Now, by my logic, I reject the weld. Finished.
Underfill.
No. No. Continuous, it's a continuous undercut. How did this concept of undercut come? See, all these things have come, the rules in the code were based, many of them, on manual welding. Right? This is a submerged arc weld or automatic weld. It is not a manual welding. When I do my SMA welding, I am a welder. I have a hand and I am trying to do a good job. But somewhere, for some reason, due to some disturbance, I get shaken and a localized undercut may happen. I continue, change my electrode, keep doing the whole weld. So the first thing I must see is what is the general appearance of the weld. Is it generally like this? No question. It's wrong.
Make proper angle.
Whatever he has done, this is not angle related, it is heat input related. So, occasional. So now how occasional is again not defined in code. So you can say, okay, 2 inches in 12 inches, something like that. In pipeline standards, you'll find something like that. 2 inch in 12 inch, not more than that and all that. What if it is 2.1 inches? I don't know, but that's what's written. But generally, if my weld is looking good and I find a local area where something happened due to which the undercut happened, I will simply say, okay, let's assess it. If it's okay within that limit of thickness and depth, I will accept it, leave it as it is. If it's not, then I have to fill it up. But I will not tell him to do the whole weld again, unless it is something showing like this, where the whole settings appear wrong. That he has done it in a hurry to finish the weld, done a high current, and he has made a mess of the whole weld because my properties are now in question. Is indeterminate. Let him prove to me by doing another sample with the same properties, with the same undercut weld on a test piece and test it, and I'll accept it. Is he willing to do? No. He'll say, no, you accept it this time. Next time I'll not do it like that. No next time comes. Okay, now I think we can break. It is time for our lunch and then we start with the welding processes. Sorry, I couldn't take your call. I'm in a training program actually. Yeah, yeah, yes, with lunch break.
Post sitting creating interpass
Which talk from? नहीं अब सब ठीक हो गया है ना कि वापस प्रॉब्लम है no, the pumps are they have been all repaired and the panels were giving problem and that's all okay now as far as I know. No, see, there are two pressure pumps for the 18 to 20 floor and they have got a controller and a panel. And they automatically, when you open a tap, the pump starts and gives you high pressure water. And there are two pumps, they work alternately. So sometimes the panel gives a problem, one pump doesn't work, then we have to reset it to the other pump like that. That is all, nothing more. It's automatic. That we can set for one pump to work or we can set for two pumps to work, everything is there. Once it is set, it is set. We don't do here. No, nothing at all. It is part of the system. और ठीक मैं वाशी में हूँ ट्रेनर ट्रेनिंग welding okay yeah. Mr. Ball किधर है Yeah, see, this 1503 is unrelated to what I talked about just now. I guess this is part of the regular 17 floors which are under the common tank and we all get the same water. उसका local problem होगा और कुछ नहीं. He has been complaining since yesterday also that the plumber has to see. Nothing we can do. Yeah. So, yeah, ready.
Come, let's go to the office. I'll show you the office around. What's that?